Hello, good morning to everybody. Again, welcome back to the plenary section. This morning we have a wonderful talks, but I do need to do two announcements. One is about the returning trip. We're going to give you the instructions. We know that some people will return on Saturday. We arrange, and we're going to have a few vans going to airport in specific time. So if you want to join and take advantage of somebody deliver you in the airport, you're going to have to go on the time we are scheduled leaving from here. Okay? That will be announced. And we cannot do the same operation of before, so we're going to have a fewer van going, but if you want to rest a little bit in the airport, eat something before going to the plane, you still be able to use our offer of transport. Okay? So just hold. For the dinner, tomorrow we have a pizza night with special soft drinks. Remember, we cannot serve alcohol here, only soft. Nobody defined to me what's soft, how soft it is. So please come. Yesterday we had a wonderful evening with close to, I don't know, more than 200 people in that room eating and talking. So join the pizza. Brazilian pizza. Remember, this city was founded by Italians, basically. So pizza is a serious dish here, right? You see the names in the phone book, you do not know where you are, near Italy or near. So be there. And for the dinner on Saturday, we're going to put the map. Everything is near. You are welcome to leave your hotel and take a Uber and go or walk. But we're going to have, I think, 2 vans leaving from here to take you and then delivery here at night. Okay? So what else? So I think those are the 2. But if you want to use the van leaving from here for the dinner, you should put your name because we want to know more or less how many people want to go in the van. The dinner, you don't have to pay anything for the dinner. Everything is paid. If you have your wife with you, that's the moment to bring. If you have a companion person, bring. We're supposed to accommodate more than 300 people in that restaurant eating the Brazilian barbecue. Okay? Now, today is 4th of July. How many Americans we have in the audience? Stand up. Come on, stand up. We are so good friends of the Americans that we appreciate the celebration of their day. So I invite you all to give congratulations to the Americans for their National Day. So please join me in congratulate them. Of course, 14th of July is another day. I did not forget. Oh, you live in 13. Okay, so on the 13th, I will invite our team here in the lab to take Hélène to celebrate, the French National Day too. Okay, so for the Americans, congratulations. We hope that the world gets better when more people have the freedom, right? Real freedom. So we're going to start now the section. The first speaker, I think everybody knows, is Zora Shlyapnikov. He doesn't like me to call him Professor Shlyapnikov, but I know him for a long time. I was a student when I first met Zora, and he's going to give a wonderful talk, you can see. Novel phase transition in disordered quantum system. has a lot of interest nowadays, disorder, non-equilibrium, all that. So we all appreciate that he took a long flight to talk to us today. So let's start this without further delay. And Gustavo is not here. So if I have to leave, one of the people, Gustavo is here, he's going to share. We have to try to keep the timing within 5 minutes so we don't delay for all the other stuff. Okay? Thank you very much. Zora, you can go.
Good morning, everybody. Do people in the last rows hear me? Hear me well? Hopefully, yes. First of all, Van der Leyen, thank you for very nice words which you pronounced, yes. And second, I'm grateful to the organizers of this conference, which is again you and several other people who invited me to Brazil, yes. I think I have been to Brazil 4 or 5 times before, maybe 5, yes. And I visited many cities in Brazil, like Rio de Janeiro, São Paulo, Natal. But for the reason which I do not understand, I have never been to San Carlos before. Do not know why, but that's what the situation was. Now, let me turn to my talk. I will tell you about novel physics and novel phase transitions in disordered quantum systems. Here is my affiliation. Oh, why it doesn't? Okay, technical problems are solved. Yes, here are my affiliations. Yes, I was many years in Paris, and I still am partially there. But I am also a group leader at the Russian Quantum Center in Moscow. Yes. Now let me start my talk. You know, we find disordered quantum systems with disorder in many cases, yes? Then there is a natural question, why do we study these systems? First of all, there is a search for novel many-body states where outer-cold atoms in disorder are especially interesting. And then there is applied and fundamental interest to these things. So I continue. So just a few words, especially for young people, about many-body system in disorder. You see here, these dots, these are particles, let's say atoms or electrons. And the curved line, the curve just represents a disorder potential, yes? So, when we have many particles in disorder, there is always a question of transport and localization properties. And there is a wonderful work of Anderson in 1958, where he said that there is the effect of the so-called localization, Anderson localization, where destructive interference in the scattering of a particle from random defects, which are this line there, leads to the localization of the wave function in a certain distance scale. Yes, this is called Anderson localization. For non-interacting particles, let me first mention here one important thing, which is important for young people. Anderson localization is a single particle phenomenon. I put a single particle in this disorder potential, which is expressed by a curve in this figure, and then I see Anderson localization. Then I put 2 particles, 3 particles, 10 particles, not interacting with each other, but interacting with this disorder potential. Absolutely the same thing. Yes. So please keep in mind that Anderson localization is a single particle phenomenon. There will be many more interesting things about this later. What is known about Anderson localization in disordered quantum systems, and what is already found in experiments? Because, myself, I'm a theoretician, but what I usually do, I say that the phenomenon is established if there is a clear experiment showing it. And regarding Anderson localization, which I just said a few words about, people in the last rows, do you hear me? Yes? Okay, good. If you don't hear me, just tell me, stand up and say, roar, 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 roar. So what is known? Anderson localization of light, of microwaves, sound waves, electrons in solids, and since recently, or since fairly recently, Anderson localization of neutral atoms. Then, just a short remark before the rest of the talk, that in 1 dimension and in 2 dimensions, yes? Okay. From here it doesn't work, but if I go there, you do not hear me. Yes? All single particle states are localized for short-range disorder. Yes? Huh? Now, especially knowing that there are many people in this audience which do cold atoms, yes, about experiments with cold atoms in disorder. First experiments observing Anderson localization of cold atoms had been performed by the groups of Elena Spe and the group of Massimo Inguscio in 2008. Some time ago, I was pronouncing the word recently. Now 2008, it's 16 years ago, which is not very recently. And after that, there was a variety of experiments, yes, in the groups of Elena Spe, in the groups of Inguscio and Modugno, in the group of Tillman Esslinger, Brian DeMarco, Emanuel Bloch, etc. Yes. What they studied are transport properties, resistance and superfluidity, and so on. But what I would like to say is something which everybody will understand. How did people reveal Anderson localization of neutral atoms? There is a very clear experiment. So imagine that there is a harmonic potential in 1 dimension, and in 2 other dimensions, particles are confined to almost 0-point oscillations. Then what I do, I superimpose a disorder potential. This red line wiggles. Optical disorder, yes? So the system is in a superposition of 2 external potentials, harmonic potential and disorder potential. Yes? And then if we do nothing, what the disorder does, and we assume that the disorder is not very big, the disorder introduces small modulations of the condensate density. Yes? People who do condensed matter physics, don't be surprised that I pronounce the word condensate here. You know, harmonic potential, which means finite size of the system. We know that in one dimension there is no Bose-Einstein condensation in free space. But if there is a finite size of the system, there is a Bose-Einstein condensate. Yes? So that's why I pronounce here the term condensate. Now, what I do, I switch off the harmonic trap. Exactly in the same way as in the first experiments of Eric Cornell, Carl Wyman, and Wolfgang Ketterle. So what happens is that no confinement. The gas starts to expand. Yes. Then, when the density in the tails is already quite small, these are more or less single particles. And what we have is the scattering of single particles from the disorder potential, these wiggles, black wiggles. Yes? And we know, I especially made this remark, that in one dimension, in disorder, all single particle states are localized. And we get the same here. After many scattering events, we get stationary tails of the density distribution. In the middle of the sample, the life is slightly continuing, but the tails are stationary. And what Alena Speck group has done, they have measured these stationary tails in the experiment. Yes? And of course, theoreticians were all the time around, yes, and they of course explained everything, yes. Even in this case, theoreticians did their theoretical work slightly earlier than the experiment, almost at the same time. So what we have a stationary density distribution. That's how, here it is. This left figure shows the density distribution after some time. Yes? So that's how people have measured Anderson localization in the experiment. And the experiment of Massimo Inguscio was similar to that. Now I come to a very important point. We study disordered systems and study Anderson localization for many tens of years. And what we were saying is that localized states are localized states and extended states, which means not localized. People, during several tens of years, people were saying that all these states are ergodic. Yes? The thing is, except for the border of localized and extended states in 3 dimensions, the so-called mobility edge, where it has been found that the state is non-ergodic or multifractal. So then, you know, our life was continuing, and already starting from 2012 and so on, so forth, yes, several groups were studying various disordered systems, like the Berthollettis, random matrix models, and so on. And what they have found that there is a finite width band of extended but non-ergodic states, yes? So we were thinking that states are ergodic, yes? And the ensemble average is equivalent to the special average, yes? But then, for some artificial models, people found that no, there are finite width bands of extended non-ergodic states. And there is a great interest, what are physical systems with extended non-ergodic states, and is there ergodic non-ergodic phase transition? So there exist extended non-ergodic states, there exist extended ergodic states. Is there a phase transition or not? First of all, about physical systems. Imagine that you have an optical lattice, yes, and you have polar molecules randomly spaced in this lattice. These brown dots are polar molecules in the ground low vibrational state, and the red guy is a polar molecule in the first excited low vibrational state. Yes? Actually, what happens is yes, thank you very much, but the pointer does not work. This red guy can be non-radiatively transferred to brown guys, yes? So, and the amplitude is inversely proportional to the distance in the power 3. And you have such a system for nuclear spins, Rydberg atoms, NV center and diamonds, and so on. Long-range hops, Levy flights, yes? So the excitation can be transferred. Then what we can do, we can try to solve this problem. What are the properties of the system? How all this happens? And that's what has been done by Boris Altshuler, Xiaolong Deng, Louis Santos, and also myself. Also fairly recently, 8 years ago. So, there is a Hamiltonian theory of diagonal. Okay, you don't hear me, you will hear me clearly now. Yes.
I can change it for you if you stay there, if you want to.
Okay. This is the Hamiltonian. This is the amplitude of the excitation transfer to another molecule. Yes. And then what people can do, they can do exact diagonalization considering from 100 to 1,000 realizations of disorder. Yes. And then we can extrapolate the number of molecules to infinity, because on a computer this can be done for n number of molecules up to 80,000. You know, here at this point, yes, I should say that it was a remarkable study using exact diagonalization. I would say that only Chinese can do this. Yes. Okay. So, what do we want to calculate? What do we want to study? Yes. Now I can. You may even stay with me. Yes. And ask me nasty questions if you have them. Yes. So, first of all, what we do, we study the ratio of the minimum to maximum level spacing, yes, which is a very important point. For localized states, we have a Poissonian distribution of this R, yes, with the average value 0.386. For extended ergodic states, we have Wigner-Dyson distribution with R average 0.53. Then, what we also do, we study moments given by this formula, IQ, yes, and for extended ergodic state, this quantity tau is Q minus 1, and for localized states, tau is 0. And we also introduce the so-called fractal dimension, dq. Yes. I had a long discussion about fractal dimensions this morning. At 6 o'clock in the morning, when you were still sleeping, there was a PhD defense of my PhD student in Moscow, in which I was participating online. Yes. After that, I even had time to have a small breakfast and then come here. Yes. So, this guy, fractal dimensions, they depend on Q. In principle, they can depend. And then we have a multifractal psi, the wave function. Yes. So, for localized states, this dq is 0. For extended states, they're in between 0 and 1. For extended ergodic state, dq is 1. So then, what we do, before I say about the states of the system, let me show you the picture. For people which do not do disordered systems during their life, I simply show the eigenstates. So imagine that we have our initial integrable system, and then we introduce the disorder. Then weak hybridization between the states of the underlying integrable system, when it mixes only a small number m of its states to form a particular eigenstate of the non-integrable system, eigenstates are localized. dq is 1. In the opposite case, where this m is of the order of the number of particles, we have an extended ergodic state with dq1. But there is a third case where the eigenstates of the non-integrable system are extended but non-ergodic, which means that this m is n in the power alpha with alpha smaller than 1, and we have fractal dimensions in between 1 and 0. The number of particle states entangled into each eigenstate tends to infinity with n, but remains measure 0 compared to the total number of particle states. That's what the situation is. Okay, so what about the system that I showed you? About this system? Yes? In 3 dimensions, these dipolar excitations or rotational excitations, if you wish, all states are extended. Yes? And the energy scale of the order of the hopping at mean interparticle separation is a good quantity to study. When the ratio of energy to this guy is smaller than 2, we have extended ergodic states, yes, and then, as you see, this curve, R is decreasing. The states become still extended but non-ergodic. It's another picture. So, what do we have? We have a possibility of extended non-ergodic to extended ergodic transition at a given rho, which means energy at the mean interparticle separation, by varying energy. Yes. There is also a possibility to have this transition at a given energy by varying the density of these particles, yes, by varying rho. Why do I say that extended ergodic to extended non-ergodic is a phase transition? Why do I use this term? For a very simple reason. If I calculate d2, the fractal dimension d2, then it at least has a cusp at the edge between extended ergodic and extended non-ergodic state. So, how do I identify these extended non-ergodic states? Well, experimentally, the lattice with 10 to 6 sides and rho up to 0.3 is possible. Then what you do, you create a dipolar excitation in a particular site, yes, and then you see what happens with the excitation, because you may detect it experimentally. And then, for the non-ergodic case, the broadening of the wave packet is much slower. And then what you do, you measure the return probability P over T after time T. In the non-ergodic case, P over T decays with increasing time much slower. Here you see the picture. These are extended ergodic. This is extended time. This is time. This is the return. So for single particle excitations, experimental detection is fairly straightforward. Of course, what you have to do, you have to create such a system. Then you have to be able to measure these are molecules in the ground and excited rotational state at a given site and so on. But that's what, in principle, is possible to do. Now, I will, because probably, where is our chairman? 10 minutes? Okay, that's fine. Hopefully, that's fine. So, then people, of course, were very much interested in what happens in many-body programs. Because since the time of Anderson, we more or less knew what is Anderson localization. And then there is an interesting question of how the interaction between particles changes the situation. And there are groups, experimental groups, which started to study this problem. First of all, Marcus Greiner group at Harvard and Emanuel Bloch group in Munich. These people were able to create the atomic microscope so that they can just fit a single atom in an optical lattice and know in which state it is. And here, just for your information, I show you the results of the experiment of the Emanuel Bloch groups. So what you have is very simple. You have optical lattice, then you put atoms, yes, and you put a wall between the left side and right side. This wall prevents particles from the left to go to the right. And then what you measure the difference in between left and right number of particles after some time t. And I think that t is in my case 150. I forgot what millisecond. Then you see these curves, yes? You see the curve where this difference, the lower curve, is practically zero, and you see the curve where it is not small. And then it is possible to establish the border of localization. And from this experiment, they say that the border of localization is more or less here, yes, where delta is the disorder strength, yes, is 5.5 G, where G is the tunneling rate. That's what the experiment is about. Now let me continue with the many-body problem, otherwise I don't have time. What people are interested in, they're interested to know what kind of problems is it good to try to calculate on a quantum computer. Yes? And of course, we understand that if the number of particles in the system is very, very large, yes, then the classical supercomputer is not able to solve the problem. And the number of steps that you need grows exponentially with increasing the size of the system. But there is a border, yes, below which the classical supercomputer is okay, and above which it's not able to solve the problem. And therefore, what we can do, we can try to use, let's say, the existing prototypes of quantum computers. They already exist, some small devices. Or what we can do, we can use the so-called quantum simulator. Quantum simulator is a system which models your original system, let's say electrons and solids, and you model them with cold atoms in a lattice. And then you study how this quantum simulator is developed. And here we see a very interesting thing, that the implementation of quantum simulators requires prediction-making models. And here I just write the Hubbard model with disorder. The first term is the tunneling rate. The second term is the interaction between particles in a given site. And this term, yes, thank you very much. Next time, please shout louder. Yes. And here, so this is the interaction between particles in a given lattice site, and this is the energy of a particle in a given lattice site. Yes. So what is interesting to study is the Hubbard model for atoms in 1D and 2D lattices with on-site disorder. Yes. For example, then, so here I show you the 1D Hubbard model with on-site disorder. Yes, black dots are atoms and white ones are empty sites. And for simplicity, what we have done, I know. And here, what we have done, we did calculations for the system with an infinite on-site repulsion. Yes, then for potential or spin-independent disorder, and we considered spin-up and spin-down particles, atoms in different internal states, all eigenstates are localized. The same thing for the same Hubbard model, but with a magnetic field. V is the magnetic field, W is potential disorder. And then we see that we have a band of extended states, extended non-ergodic states. Calculations have been done for infinite on-site repulsion, L lattice sites, and L divided by 2 particles. And here you see that L equals 24 is a possible border of quantum advantage. Yes. Why I say here possible? Not because I have doubts whether people can calculate for 28 or not. Yes. Maybe on an American supercomputer they can, not more. But I do it because of Peter Zoller. Him and his collaborators said that, of course, you may establish the border, but this is only for the case of an ideal Hamiltonian, which you use for the quantum computer. When you allow a disturbance of the Hamiltonian, the situation can change, and then the prototype of your quantum computer has a problem. We are now studying this type of systems for, let's say, various types of situations. But in an ideal case, 24. So, I was told by van der Leij very kindly that I have 3 minutes. Now it's probably 1 or half a minute. That just a statement. More than 60 years since the discovery of Anderson localization, we were considering only one transition in disordered systems. Anderson transition. Localized state, no conductivity, extended states, ergodic extended state, there is a conductivity in the system. But presently, a bunch of transitions between extended non-ergodic state and in particular a transition from the extended ergodic to extended non-ergodic state become reality. For single particle problems, this is already established theoretically, and for, let's say, many body systems, of course, we have a problem of the size of the system, but there are possibilities to avoid this problem. I'll give a talk at the seminar of section 6. Oh my God. Okay. And I'll tell a bit more about that. Yes? So, at any event, we expect novel phase transitions in disordered quantum systems, and many of them. Yes? This is after more than 60 years of the studies of disordered quantum systems. Now, conclusions. The conclusions are much simpler than the talk. Thank you for attention.
Thank you, Gora, for the very nice seminar. Do you have questions?
Great insights, Gora. Thank you. Great talk. So you said, at least you had it on your slides, that D2 behavior is at least a cusp, yes, suggesting that there may be a more dramatic behavior.
Yes, you are right. You are right. There is at least a cup, but also there can be discontinuity.
Which is indicative of what? I mean, when do you expect a cusp and when do you expect discontinuity versus cusp?
Let me give an honest answer to this question. I don't know.
Good, thank you.
More questions?
People from the lab. You, van der Leij, have a question.
What are the intrinsic limitations that prevent us to have a localization in 3D?
You mean that in some cases, when I include interaction, I destroy
Let's
localization?
forget about interaction for a moment.
Uh-huh.
Is localization restricted to 1 and 2D, or we can have in 3D?
Yes. So what I said somewhere close to the beginning of my talk, that in 1 dimension and in 2 dimensions, whatever small the disorder is, all single particle states are localized. Probably I had to add one more line saying that in 3D there is a Joffe-Regel criterion. The states with sufficiently high momenta are delocalized, and with lower momenta they are localized. So in 3 dimensions there is a possibility of both. extended states and localized states.
Okay, thank you. And more questions?
People from the last rows, did you understand what I was talking about or not? You did? Okay.
Do we have in nature phenomena of localization naturally?
In nature,
Yes.
yes,
With
of
light,
course.
for instance.
Yes, people observed experimentally localization of light, localization of electrons in solids.
No, but in nature, like I read a paper some time ago about the wings of the butterfly because of the nanostructure and disorder. There is localization of light. Is this a common? Is this an effect that the nature knows before Anderson, or?
I do not know what nature knows and what it does not. Yes, but I would say, because the nature did not tell me about that.
Okay.
But I know for sure that in nature there are systems where the localization is present, and the idea of people was to find it. And they have done it for light, for electrons and solids, for cold atoms. Yes.
Cold atoms is something we produce. In nature, my question was if in nature, in general, localization is something that appears in some parts.
Yes, for electrons and solids, where you get to a new regime and you see that the conductivity is zero.
Yeah, but okay, fine, thank you.
You have a question? Yes, please.
I can take the microphone.
Hi, Georgie. Thanks for the talk. By the way, the talk, your next talk is on Symposium 7 at 5 p.m. on Friday. Yeah, you were right, all along.
Oh, so it's not a question, it's a remark.
Yes. No. The question is, what happened if it's fermions? Is there any difference?
Sorry, I don't understand the question.
What happened in the calculations? They are all for boson.
Of course, related phenomena, of course, are present for bosons, and people have established some type of localization for bosons. Yes, this is true. If they are fermi. Oh, what I was telling you, the emphasis of my talk in the many-body part was on the presence of extended non-ergodic states. Yes? And they are present in both fermionic and bosonic. And please, now I have a question. I have a question to you, van der Lee. You said that I should give a seminar. Okay. Seminar 7. Does not matter much.
So to keep the schedule of our event, I ask you to find Gora during the coffee break and ask further questions there. Let's thank him again. Our next speaker is Grish Agarwal from Texas A&M.
Yeah. Okay, sure. Okay, so to go there.
It's not the physical, so you have to go the
Okay. Okay. Well, good morning, everyone. It's a great pleasure to be here. And I like to start by thanking the organizers, Vanderlee and Louis Davidovich, for inviting me. I'm going to discuss some aspects of quantum metrology, mostly theoretical aspects. Here is a little outline of what I'm going to tell you. So I'll start by telling you what are the limits to classical sensing protocols, why quantum light is required. It can produce better signal to noise ratio and therefore useful for quantum imaging and microscopy purposes. I will indicate how to obtain the absolute theoretical limits for a given quantum probe, starting from the quantum metrology framework. Then I like to tell you what measurements can reach such theoretical limits and what are the possible realistic measurements and the quantum probes. And I'll tell you that the time reverse quantum metrology has considerable potential, and in many cases it can saturate the Kramer-Rao bound. So in a typical classical sensor using optical beams, let's say you are looking at the transmission of a beam from the medium, and the amplitude of transmission can be used to find out the phase and the absorption in the medium. Both phase and absorption carry information on the properties of the medium, such as density of particles, absorption wavelengths, oscillator strength, relaxation and scattering parameters, circular diaphragm, etc. Small perturbations on the medium are of special interest, and therefore the question arises how small parameters can be detected, and the limit is set by the fluctuations in the laser field. So what's known as the short noise limitation, and that arises from the fluctuations in the photon number in the laser field, and these fluctuations are known to be Poissonian, and the Poissonian nature of the fluctuations lead to fluctuations in the signal, and the signal to noise ratio in that case goes as the square root of the signal, and this is the short noise limit. So question is how we can improve such a short noise limit, and we need to replace the coherent light which has Poissonian fluctuations by quantum light. So one possibility is to use the squeeze light, and one of the first results on the what the squeeze light can do for us was shown by Carl Case in the context of the measurement of phase using Michelson interferometer. So if you have the standard Michelson interferometer and you use it to measure this phase, then you can show that the sensitivity of this phase measurement is given by this, where n is the number of photons in the input coherent beam. But Cave showed that you add a squeezed vacuum from another port of this beam splitter, and then do a different kind of a measurement here, which involves detection of the intensity at this port as well as this port, and then looking at the difference of these two intensities and the fluctuations in the intensity difference. The fluctuation in the intensity difference gives you a phase sensitivity which is, well, after some time my finger stops working on this. So it gives you the improved phase sensitivity. So it gives you this improved phase sensitivity by this factor e to the power r, where r is the squeezing parameter. Okay. So now I like to describe to you little bit about the quantum metrology framework, that on theoretical grounds, what is expected. So here we have the quantum Fisher information. So if rho is the state of the system and x is a parameter for the system which you like to estimate, then one defines this quantum Fisher information So this is how the quantum Fisher information is defined, where L is this complex operator given in terms of the derivative of the state of the system with respect to the parameter that you like to estimate. And once you have this, then you can estimate the parameter delta x from this relation. It's difficult to compute L. But if you have the unitary evolution of the system, then there is a considerable simplification, and the quantum Fisher information is given by this top line in terms of the fluctuations, quantum fluctuations in the input probe state. And in particular, if the parameter that you like to estimate is given by this simple evolution in terms of u, then one can show that the estimate of the parameter is given by this quantity, where delta G is the fluctuation in the variable G in terms of the input quantum probe. And so the standard quantum noise limit can be beaten if you use a quantum probe for which this fluctuation is bigger than that for the coherent state. So that's where the importance of the squeezed state of light comes in. And here are a couple of examples, like for the phase measurement. So in this case, the generator is very simple, and the Kramer-Rao bound for the phase would be given by 1 over the fluctuations in the photon number. For the standard coherent state, you have the standard quantum noise limit, But if you use light with super Poissonian statistics, then this limit on the phase is given by 1 over mean number of photons, which is called the Heisenberg limit. And in this case, the two-mode squeezed vacuum turns out to be especially useful. On the other hand, if you have a force measurement, then the generator is in terms of the momentum operator, and alpha is the displacement. The Kramer-Rao bound would be given in terms of the 1 over fluctuations in the momentum. And so if you use a single mode squeezed vacuum along x-axis, you will beat the standard quantum noise limit by this factor. And the measurement schemes, as we will see, would be the time reversed quantum metrology schemes. Sorry. So what is the time reversed metrology? Suppose we start with some initial state and we produce a quantum probe by applying a unitary operation S. So this is the quantum probe which is used to probe the system. And so the output in general would be a mixed state. And now you carry a transformation which is inverse of this one, and then have a detection. So this scheme where you use the inverse of this transformation followed by detection, this is called the time reverse metrology. In the standard procedure, you don't have this operation. So this is the added thing in the context of time reversed quantum metrology. Okay, some examples which demonstrate this advantage. So here you have a generation of the two-mode squeezed vacuum. This could be a parametric amplifier, and in one of the arms you have a phase changing element that you want to estimate. Here is the inverse of this operation, and that can be easily performed by changing the phase of the pump which is pumping this OPA. And at the output, you look at the total number of photons at the two ports and the fluctuations in the total number of photons in the two ports. Now for experimentalists, they would typically measure what's called the error sensitivity. The error sensitivity is in terms of the fluctuations in the total number of photons at the output port divided by this derivative, and this turns out to be of the order of 1 over mean number of photons, which is the Heisenberg limited sensitivity. On the other hand, you can do a full quantum Fisher information analysis for this setup, and then you find the quantum Fisher information associated with this input state, and here is the result for the quantum Fisher information. From this you can get the Kramer-Rao bound, and you find that this kind of measurement, it saturates Kramer-Rao bound. And in fact, several months ago, an experiment from Janbei Pen's group appeared demonstrating the great advantage of this scheme in the measurement of the phase. Another example is in the context of the atomic interferometers. So let's say you have n atoms, you start all of them in the ground state, and then you apply this nonlinear unitary operation to prepare a quantum probe. So what this nonlinear unitary operation does, it produces this kind of a n particle GHG state. Then you want to sense this rotation, and then the inverse of this unitary operation and the readout. So if you look at the quantum Fisher information framework, calculate the QFI, this goes as n square, and therefore delta phi will go as 1 over n, and so you have the Heisenberg sensitivity in the measurement of phase in the context of the atomic interferometer. For the experimentalist, you can measure the final state of the outcoming atoms and look at the population distribution, and from this you can calculate the phase sensitivity, and this gives you the same result as this, and therefore again this quantum this time reverse metrology arrangement saturates the Kramer-Rao bound. Here is an example of the time reverse metrology for the case of displacement, and there is a beautiful experiment from the NIST group on what they called as the quantum amplified metrology, and actually their experiment fits very nicely in the general framework of the time reverse metrology. So what they were measuring, the displacement of the ion, and so you can start the ion in the ground state, apply the squeezing operation on the ion, produce this squeezed ground state for the ion, and the squeezing is in this direction x. Now you want to measure a small displacement, and so the effect of this is to do this. You displace this by this small amount. Then you apply the anti-squeezing operation, and what you find that the output again is a coherent state, but its amplitude is amplified. So you have amplified the amplitude of this small displacement by this amount e to the power r, and that's why this group called this as the quantum amplified metrology. And in the experiment they showed that for small values of this displacement, they can get an improvement of this order. So if you look at this in terms of the quantum metrology framework, that is the Fisher information, you can calculate the Fisher information for this, and from that you find this result. So you have the improvement factor e to the power minus r, and now the question is whether the standard measurement that you do for the ion motion by using the Raman pulse technique, and then you measure the phase contrast, so that gives you signal to noise ratio of this order, which in fact is same as this, but this holds only for a small value of alpha. So the question arises, is this the best measurement, or can one do something else to get the best measurement? And in fact it turns out that for the best measurement you need to do a phonon counting measurement, and if you do a phonon counting measurement, then the measured Fisher information would be identical to the quantum Fisher information. Okay, so much was for the unitary evolving system. Now I want to discuss open systems and the sensitivity for the open system. So in this case, we are looking at the absorption in the medium, and we want to estimate the parameter alpha, which is the absorption of the medium. Now in terms of the error sensitivity, you can estimate the error sensitivity by looking at the output and the fluctuations in the output, and a simple calculation shows that the error sensitivity is related to both the fluctuations in the incoming beam and the mean number. And so this expression clearly shows that in order to obtain the best sensitivity, you must have delta n 0, that is, no fluctuations in the incoming beam. And so that would be the case when you use the photon number states. And this little graph shows a comparison between the sensitivities using the photon number states and the coherent states. And as you can clearly see from this graph, that the photon number states are best for the estimate of alpha. And this result that you get from the error sensitivity calculation, in fact, also coincides with what you would get from the considerations of quantum Fisher information. But we have a problem in practice that production and detection of high photon number Fock states is extremely challenging. But we also know that the two-mode squeezed vacuum states can produce Fock states via conditional measurements. Now, this we know in theory, but again in practice hard to implement because of the low efficiency of the single photon detectors. But theoretically, we have found that the two-mode squeezed vacuum gives you the same QFI as the Fock states. And therefore, the problem of producing Fock states with large photon numbers can be bypassed by using the two-mode squeezed vacuum. So there is a full theoretical framework for calculating the quantum Fisher information using the Wigner function approach. And we know that the two-mode squeezed vacuum has a Wigner function which is Gaussian. It is also known that if such a beam passes through an absorber, the output beam is still characterized by a Gaussian Wigner function. So the QFI which you calculate for the two-mode squeezed vacuum is same as what you get for the Fock states. And in fact, it also turns out that the QFI for the two-mode squeezed vacuum is higher than that for the one-mode squeezed vacuum. So this graph shows the sensitivity plot as a function of the photon number for the one-mode squeezed vacuum and the two-mode squeezed vacuum. And you see the clear advantage of using the two-mode squeezed vacuum. Excuse me, how am I doing with time? Okay. Okay, so that's the theoretical result with the two-mode squeezed vacuum, which is now the best. So again, the next question is, what measurement would satisfy QFI? So what we need to measure in this case is the joint photon number distribution of the two modes. So PNM is the joint photon number distribution for the output, and you can calculate the Fisher information, that is the measured Fisher information with the output field, and calculations show that this measured Fisher information is equal to the QFI and therefore this measurement will saturate the Kramer-Rao bound. However, in practice, it's difficult to measure the complete joint photon counting distribution, and so we have to do something else, and that's where the time reverse metrology turns out to be useful. So here is again the time reverse metrology setup. We produce the two-mode squeeze vacuum here. Two-mode squeeze vacuum here. In one arm, we have the absorber, and then we have the inverse operation. And at the output, we look at the total photon numbers and the fluctuations in the total photon number. For small values of the absorption, what you get from the QFI and this kind of measurement of the error sensitivity, they essentially coincide with a little larger value of the absorption. This measurement gives a result which is quite close to the Kramer-Rao bound. So again, it's an advantage to use the time reverse setup. So here are the results for the theoretical results for the estimates of the gain parameters, optical gain parameters, and results for two different schemes, the balanced photo detection and the SU11 or the time reverse setup. And the graph at the bottom shows the advantage of the time reverse setup. So in the remaining time that I have left, I would tell you some of the experiments that our group has done, and we produce what is called the intensity difference two-mode squeeze light using the four-way mixing in the rubidium vapor, and the amount of squeezing that we produce is about 6.5 dB. This is the intensity difference squeezing. In other words, this quantity A, which is the intensity difference fluctuations, these are lower than what you will have for coherent beams of light. So one of the first applications that we did, we demonstrated the quantum measure advantage in the absorption measurement, and the measurement shows here that for low values of the absorption parameter, we demonstrate a quantum advantage of about 1.2 dB, and this is because we have other losses in the system, and if you calibrate for the other losses in the system, then the measured advantage would correspond to 3 dB. So we did another experiment using this two-mode squeezed beams of light, and that's in the context of the Billion scattering. So what we do is we use one of the these are the probe and conjugate beams which are quantum correlated. Sorry. So one of these beams is used as a probe for the Billion sample, and then the Billion sample has a pump, a separate pump, and then we look at the advantage in the Billion imaging or Billion microscopy of using the quantum. And at the bottom, I show the Billion gain spectrum. Yeah, I will return soon. So what this graph shows, the advantage of using the squeeze light over the coherent light. And if you look at the graph at the right, this is for the low pump powers of the Billion sample. And if you use the coherent light, then the signal is buried in the noise. Whereas if you use the squeeze light, then you can still see clearly the signal because the noise flow is much lower. So the advantage is plotted in the graph on top. So signal to noise ratio, and the blue curve gives you the result for using the squeeze probe beam versus the use of the coherent beams for different values of the pump power. And so an advantage of about 3.4 dB is established in this experiment. So we use it further for demonstrating in principle a quantum imaging using these intensity difference squeeze beams of light. So here are my conclusions. So I have demonstrated how the squeezed states of light and matter can be used to our advantage in quantum metrology, and I have demonstrated the special advantages of using the time reverse quantum metrology and some experimental results using the intensity difference squeezed beams. Thanks for your attention.
Thank you, Dr. Agarwal. Time for questions.
Thank you, Girish. Wonderful talk. So, for some tasks, I can saturate my Kramer-Rao bound with a completely classical method. I can define certain settings, certain tasks. I can give examples, and then I can saturate the Kramer-Rao bound, achieving quantum fusion information, nominal quantum fusion information, with a completely classical method. So your conclusion that your two-mode squeeze state saturates the Kramer-Rao bound as well as the Fock state is probably limited to certain, perhaps vast, but still limited class of problems, limited class of tasks.
Yeah,
Can you define this class of tasks within which?
My tasks are well defined. Is the measurement of the phase, measurement of the displacement of the forces, and the measurement of the absorption parameters. So these are the three kind of parameters that I can study, and I can saturate Kramer-Rao bound, and in some cases, particularly for open systems, I nearly saturate Kramer-Rao bound. For small values of the parameters of the open systems, and in any case, in practice, you are only interested in looking at the small values of these parameters.
Hi, thank you for the talk. In time reverse metrology, so you apply this unitary operator, and then the whole scheme relies on the fact that you need to apply the inverse of that operator. So I'm wondering how robust is the scheme that you apply these operators perfectly? Because experimentally, there's going to be noise in the applied unitary operator and also on the inverse of the operator as well. So how robust is the scheme to imperfections in these operators?
Well, we have estimated the effect of some informations like some additional losses, and we have results and we have shown that it works very well. Yeah, Vlad.
Thank you, Girish. Okay, so just a quick question. So what is the fundamental limit for squeezing?
Fundamental limit of squeezing, well, for us, we are limited by the kind of densities that we use in our experiment. Because if you want to increase the density, the squeezing increases, but then you have collisional losses, which kills the squeezing. So that's one of the factors in atomic vapors, which is limiting squeezing.
Thank you, Girish. Nice talk. I was wondering, you spoke first about the measurements also for at the end, that you do the joint measurement, the photon numbers, that you need number resolving detectors for that. And then you went to the difference in the intensity fluctuation strategy. So I may lose something. I was wondering, can you saturate the quantum Fisher information? Do you need number resolving detector, or you can do different technique in the measurements, and how the losses affect the saturation and the Heisenberg scaling?
There are two things. One, most of the theoretical part that I described was using the two-mode squeezed vacuum or one-mode squeezed vacuum. But the experiment that I described, they were using the seeded squeezed vacuum. And experimentally, it's easier to work with the seeded squeezed vacuum. And what we demonstrated in the squeezed vacuum, and that's an experiment, that there is still quantum advantage, but quantum advantage would not be as much as you would expect on theoretical grounds. It's much lower because, as you know, in the experiment, you have to beat with other kind of problems like Dennis was asking.
And do you need the number resolving measurement to saturate the quantum Fisher information in your model?
Squeezed vacuum results that I described, I said that SU11 interferometry gives you results by doing the error sensitivity measurements, which are almost identical to what's predicted from the Kramer-Rao bound. So you don't need number resolving detectors there.
Thank you.
More questions? That's it. I have a similar question. Thank you, Girish, for beautiful talk. Similar question to Vlad's question. So what is like final limitation? Why you only have 3 dB win? Why it's not 6? Why it's not 30? Why it's only 3? Because in your original formula, it looks like you can go like forever.
Yeah, I mean, because of the experimental imperfection that basically is the reason, and the detection efficiencies. Detection efficiencies are never 100%. Like in the experiments where we were using the CMOS cameras, the CMOS camera is very, very low detection efficiency.
Okay. One last question by Gustavo.
Thanks, Gary, for the inspiring talk. I was wondering about the Brilli 1 experiment. It's curious that you have this very fine matching, right, of the narrow band of your squeeze light source and the brilliant gain bandwidth, right? Could you comment on that? I mean, there's previous experience with Raman, right, from Warwick Bowen's group in Australia. But with Raman, the gain is so broad that you don't need to worry about that, right? You always have pretty much any squeeze light source could do the work. I mean, is this a coincidence, or you actually targeted these experiments because of the narrow band source of your squeeze light?
Yeah, I mean, basically when we first started and talking to Blad about it, so the idea was that since we have a narrow band squeeze light source, so, billion experiments would be especially good to start with.
All right, to keep the schedule, let's thank Dr. Agarwal again. And we return at 11:15 sharp.
We should go to the coffee and then return in the time of the restart. And the people that has poster should be hanging the poster already, because today after 4:30 there is no more section, only poster, so people can, but it would be nice if you put your poster already. It's there prepared for. Thank you.